Good afternoon, good evening, good morning, depending on where you are in the world. Welcome to this webinar, organized in collaboration between Eaglet Eye Academy, and Alden. And we're absolutely thrilled to have a guest speaker today in the form of Dr. Jason Jetlicka, and he will say a few words on Zenlens and the potential for corneal scleral measurements in the fitting process. And after that, I will take over. My name is Arnold Snapfingers, and I will show you through a few case examples how the fitting can be done at this moment. It's my pleasure to introduce Jason to you, Dr. Jetlicka. If you could take over and present your slides, please. Thank you.
Thank you, Arnold. It's great to be here, and it's a pleasure to be able to talk about working with Zenlens with the eye surface profiler and some of the exciting things that are happening and which will continue to happen in the near future. So just as a brief introduction to the concepts that we'll touch on and Zenlens and the use of this technology and the assistance, for those of us who fit scleral lenses, it's really the three-step process, and that's vaulting the central cornea, clearing the limbus, and aligning the sclera. And really anymore, especially working with Zenlens, vaulting the central cornea should never be a difficult task. It's a simple matter of putting on a lens that's the proper depth, and you're going to find the appropriate vault. The second aspect there, again, is clearing the limbus. And again, this should not be that difficult. If we put on a proper geometry lens, if we put on a reverse geometry on an eye that needs it, or a standard geometry on a standard eye, we're going to be pretty close to having limbal clearance without a lot of effort. But if we need more or less, we simply just ask for that when we have the lenses made. I think the biggest challenge for me personally, I think for a lot of scleral fitters, from what I hear from people's questions they have about managing patients, a lot of it is getting that proper scleral alignment, getting that lens to contour the sclera properly to provide comfort, a good fit, reduce debris and excessive tear exchange, avoid compression and things like that. So aligning the sclera is really kind of the biggest challenge, I think, in getting good scleral fits routinely. And it's, to me, again, it's the thing that takes the most time and effort and really expertise and doing this for a period of time to get good at that. So again, just briefly on Zenlens, again, the basic first two steps of fitting should be easy with this design, because as long as we're choosing the proper geometry and diameter, we're going to clear the limbus, we're going to align the cornea relatively evenly with just the diagnostic set out of the lens, or diagnostic lens out of the set, then again, that part becomes straightforward. And there are, of course, times we need toric peripheral curves because we've got toric scleras. That happens to be probably more than half the time. And so the basic set does have the toric peripheral curve option in the diagnostic set to identify how to properly fit those a little bit more readily than not. But again, there's still the fine-tuning of the peripheral aspect of the fit is a challenge. So again, Zenlens makes the basic parts of fitting very straightforward, easy to fit, make adjustments, raise and lower the lens as needed in any aspect of the lens. Again, the challenge is that to get that lens to align perfectly, we know that because the scleral lens vaults the cornea, we don't have to be precise with how we fit over the cornea, but we really do need to be pretty precise with how we fit the sclera if we want an optimal fit. And the advent of scleral topography in general goes a long way in helping make that happen. It certainly reduces the fitting time. We can immediately know whether we need to be reaching for a toric diagnostic lens or not. And just, again, scleral topography is a real breakthrough. And even though there's a time spent to obtain it, the time that is saved in the fitting process just really streamlines the scleral lens fitting process to have scleral topography as a tool for the scleral lens fitter. And so, again, what the next stage in the evolution of lens fitting to me is to say, instrument has all this great information. There's really no reason, because scleral lens fitting is just very scientific, and it's, very much math and geometry, what we're doing here, that there's no reason that the software can't do a lot of the detection of what type of peripheral curves to put on a lens to get a much more precise initial fit. So if the software can not only measure the shape of the sclera, but then using that data can tell us essentially really a first lens, an initial lens fit that's going to be very close to optimal right away, it's going to save a lot of chair time. It's going to save the patient's time. It's going to give the patient a better impression. I mean, everything about it is positive. And it's going to allow the practitioner to spend more time focusing on just working on the very fine details. It's also going to allow them to see a lot more lenses on eye that are more optimally fit. So they're going to, even as the software is doing a lot of work, I feel like it's going to allow the practitioner to become a better practitioner faster. I don't think the software takes away from the skill. I think it adds to it, in that practitioners are going to get used to seeing better fitting lenses, and they're going to know how the lens should look more often. So that's the exciting part of using the software. So again, what we're here for tonight is we're talking about integrating Zenlens and the iSurface Profiler, and the software that is being developed to utilize the data obtained by the iSurface Profiler in designing, fitting, adjusting Zenlens scleral lenses is really great. It's happening. It's improving quickly. Again, the scleral fitting process in general is just very methodical. We're choosing diameter off HVID. The software can do that just as easily as we can. Choosing the geometry off the shape of the eye. The software can do that just as easily as we can. Choosing the SAG and the peripheral curve system, again, all this is very straightforward and can allow us to get a lens very close to optimal and let us focus our expertise on fine-tuning that fit and getting it just further optimized. So again, it's really a great synergy to have the iSurface Profiler and this software that's being developed integrating with fitting Zenlens. It's exciting to be able to make this process faster and better for our patients and better for our practices. So I'm going to turn it over to Arnaud and let him continue with our evening here. Get to the right place. I think we're in good shape. Okay. Arnaud, do you want to take it over from here?
Okay, yeah, great. Thank you so much, Dr. Jetica, for giving this very clear picture. Let me just switch to the other screen. Bear with me. Excuse me. Yeah, slight glitch here in the technology. I just okay. Here we go. Okay. Good. So we should have the. You should see the slide, the first slide now.
Yep, looks good.
pointing out the most important things that we would like to contribute with the device is actually to hand more power to the practitioner and enable them to fine-tune the fits and get the routine tasks of the fitting process to help out with that and speed that up. And before I go to a few case examples, I'd first like to show a little bit on the technology that we use for this device, which is called profilometry. And basically, the essence of it is that we have an eye. On that, we project a vertical line pattern, as you see here. And these photos then are processed into a 3D height map of the eye. And so we basically, in this process, take 2 photos in rapid succession, so that's a few milliseconds, and it'll give you a 3D perspective of the shape, the front shape of the eye. And that is what profilometry does. It describes the front shape in height to our users. So what does that mean? It's one fast measurement. There's no stitching needed. It's highly accurate. So corneally, it's about 2 micron in accuracy, and for the sclera, you should think about 10 micron. It's a validated technology as well. There's now, at this moment, 7 peer-reviewed publications on it, and of course, we're happily collaborating with researchers to support them into publishing more, and there's a good number on the way as well. And at this moment, we have about 25 lens designs in our database, so with first lens fit algorithms. Benefits, as Dr. Jetica already mentioned, is that we help to do the fine-tuning of the lens fitting process, and in that we can actually save a lot of chair time for the amount of trial lenses needed before you hit the right one. And that's what we're going to do. And the best way for me to show that is through a couple of examples. So let's switch to the live software. And again, bear with me for a slight moment. And yeah, here we go. So we have our first case here. We're actually in the live software. So what you see centrally, I'll just enlarge on that, is an elevation of the sclera and the cornea. And of course, immediately visible, sticking out in red, is an elevated element of keratoconus on this patient's eye. And what we can see as well is that there is some toricity going on. So we see an elevated portion horizontally, and we see a downward dipping portion of the sclera vertically. So we suspect, just on the basis of the color of the elevation map, that there is a toricity of the sclera. You can, particularly in the discussion and the dialogue with the patient, you can show the same shape of the eye in 3D as well. And there's a number of maps that you can show. Because this is a corneoscleral system, you can actually show all of the corneal maps and parameters that you would have from your normal topographer. But today, the focus is on fitting Zenlens. So what we need to do to fit the Zenlens is to go to the tab on the left-hand side and oh yeah, bear with me. I'm going to go for the ProLate lens. And basically what the software does is automatically select the best fitting lens on the basis of the actual clearance that you want. So the volts of the scleral lens. It will calculate the landing zone so that it aligns properly with the actual shape of the sclera, and it calculates the toricity. All of that is done automatically. I'll see if I can enlarge that. No, that's not the case. Okay. And so this is one example of a keratoconic eye with significant toricity of the sclera, where the system automatically measures or fits the optimal Zenlens. Let's switch to a second example. What we see here basically is corneally significant toricity, and we can see that on the right hand side already, because there is a good amount of astigmatism, 5.8 diopters of astigmatism measured. But we see no keratoconus, so otherwise it is it seems to be a healthy eye. And what I would like to do is to take you step by step through the fitting process. So what is the logic that the fitting algorithm from the Eaglet eye software, what does that follow? So we'll go to the tab again for the 16mm prolate scleral lens. And what we see here is that it has selected a lens with a volt sag of 4.4 millimeters. And let's go back to the results and see how that came about. So for that, we turn to the sag calculator and we fill in the diameter of the lens, hit enter, and we then look at the sagittal height, the average sagittal height at 360 degrees, which in this case is 3.97 millimeters. So 3.97 millimeters, we add 250 microns for the actual clearance that we would like, and an extra 100 micron for the settling of the lens. So plus 350, plus 350 microns would make 4.32 millimeters. And of course, for when picking the lens, you do not want any touch, so you go one higher, which is a sag of 4.4. And the landing zone, the APS-10, is basically a little bit more sophisticated and is not something you can easily calculate yourself just off the results. But what we can look at is that for the toricity here, it actually shows that it has an APS of -10. So there's a significant toric lens prescribed here. So let's reverse engineer that and see how we can see the logic behind that. So we'll go back to the results, and this time we look at the sag calculator again, and we see that the min sag, so that's the out of the 360 meridians that have been calculated, it's the one meridian where it is the lowest, so that's at 3.66 millimeters, and the max sag, it's at 4.44, and that's a difference of about 0.78 micron, so 780 micron difference. And you should realize that the APS steps are done in 30 micron increments. And so the maximum available to us is 10 flatter and 10 steeper. So that is, in fact, the lens that was selected here. And it could well be that you start off with this lens as the optimal one and then take steps to fine-tune that. Okay, let's go to the third example. The third example. So again, we're looking at a measured eye. We see that from this elevation map that the cornea looks very irregular, but there is a pinguicula on the nasal side on the horizontal meridian. And of course, one of the wonderful features of the Zenlens is that you can fit a microvolt. So how can this measurement, how can the eye surface profiler help you in calculating a microvolt? Well, for that, let's turn to what Alden prescribes or suggests that you should do when calculating a microvolt. And they describe 4 steps. First is the axis. So it's number 1. So you need to find the axis from the horizontal plane of where the pinguicula is actually located. And second is the decentration. So that's the actual distance from the apex. So let's look at those two and see how we can calculate that easily. So for the angle, all we need to do is to hover the mouse pointer over the actual the top of the pinguicula and read off the angle. And in this case, it's described as 348 degrees. And the distance is indicated as well. It's 7.90 millimeters. So we've got the first 2 bases covered already. Let's look back at the prescribed steps. So we need the width of the microvolt. And as you can see here, that's just the width of it, so from top to bottom. And we need the depth. So how high is it? How high is it sticking out? So we go back to our example. And again, we put our mouse on top. Bear with me. So there we go. And we see that the value, the maximum value indicated is 218 microns. So that's the maximum volts that we have, the maximum depth, as they call it. And to calculate the width, all we need to do is to put the mouse on the top, and it says 7.78, and subtract 7.67, and we have the width of the pinguicula. So basically, with a single measurement, you are able to get all the parameters that you need to order a lens with the right microvolts. Okay, with me. So to continue, we are absolutely very much delighted that Eaglet Eye and Alden have joined forces to make the whole fitting process for the Zenlens a lot faster, a lot easier, and more precise. And for that, we've developed this first lens fit algorithm. And of course, with the help of the feedback from our customers, we keep on improving that. and of course with the team from Alden and Dr. Jetica, of course, we're working closely together to keep on improving that algorithm. And it's something that you can use right now, right today, and of course you're very well invited to contact us if this is of interest to you. And the best way to do that is to drop me an email, info@eagleti.com would be the best way. Otherwise via Facebook, via our Facebook group. And if you have any questions or any suggestions on the basis of this webinar, then we'd be delighted to hear from you. This webinar organized by Eaglet Eye Academy is one of a series, and we will have more on this subject. In particular, we will come back on the fine-tuning element that Dr. Jetica mentioned, and show you more cases of complex eyes, complex surfaces, where and we'll explain you how you can best work with those and get the best results in the shortest amount of time. So with that, I think we've covered what we plan to cover, and we're extremely grateful for the many people who've registered, and look forward to meeting you again for one of our future webinars. And a big word of thanks to Dr. Jetica for sharing his expertise on this particular field, and we wish you a wonderful evening.
Arnaud?
Yes.
There were a couple of questions through the chat, and I think if we've got just a couple of minutes, maybe can we try to address one of these issues? Could you go back to the second case that you had up there, please?
Will do indeed. Bear with me. Okay, this one here.
Yeah. So part of the question here is, when you look at the scleral profile in this picture,
yeah,
and you look at the scleral shape from around 2 o'clock all the way around back to 4 o'clock, it looks pretty blue, and it looks, it doesn't look that toric, so to speak.
That's correct.
And even though it's very raised nasally, so there's a question, we're fitting the sclera, and the sclera itself doesn't look all that toric, but what you're measuring here is you're measuring actually the sag of the two meridians kind of independently, and that because we don't fit scleral lenses, at least not right now, with back surface toric optic zones over the corneal zone, then the reality is when we've got a significant difference in two meridians of the eyeball in general, let's not segregate the cornea and the sclera separately. Let's just say one meridian of the eye versus the other meridian of the eye that we're fitting, that we're making up for the differences in the meridians right now, at least only through the scleral zone. And so, as you demonstrated, you've got a difference in these two meridians of 780 microns.
Yeah.
And because we're not going to compensate for any of that through the optic zone, it has to occur in the scleral zone. And so, again, what the map does is it's kind of showing us the shape of the sclera a bit independent of the cornea. And so that while the sclera itself doesn't look all that toric, because the cornea has 5.7 or whatever you said it had, there's a lot of built-in asymmetry in the two meridian heights that is generated from the cornea. And the way that we're trying to make up for that, again, is through the landing zone of the lens. So, that there's just a question of why would we go 10 flat versus 10 steep on this lens when the sclera doesn't really look that toric? And part of it is the cornea. And that's one of the big challenges I think that we miss out on a lot is because we're always thinking about, well, we want to fit the sclera ideally, and that's true, but we're making an assumption then about the cornea itself that, well, the cornea at the borders of the cornea must be even in height, and it's definitely not. And so again, the concept of using the two different sag heights to help generate the difference in your landing zones is really what we're trying to attempt here to compensate for that. So I guess that's the best way I can point out as to why it works this way. I don't know, in a couple of years, maybe we're putting back torics on the cornea too, and then, maybe then we're putting less of it into the landing zone. But the point being here is that somewhere along the way, we've got to come up with a difference of 800 microns between these two meridians.
Yeah.
And the only way we can do that is with the landing zone at this point in time, at least. So
yes,
that's why the toricity of the landing zone is what it is. So.
Yes, absolutely. And if I could add something to that, what we see on display here is the difference between relative height, which in essence an elevation map is. So we take the absolute height and we subtract the best fitted sphere from that to show us a pattern on the surface. And whereas the sag calculator with its min sag value and its max sag value, those are absolute heights. They are the actual sag values for those meridians. Right. And we have for this particular case, for the scleral zone of this elevation map, because of there's some edge artifacts at 9 o'clock and at 3 o'clock, where at the very edge of the shape that was measured, there's some lift, most likely artifact, but it does influence the reference sphere of the scleral zone of the elevation map, and that's why it masks somewhat the possible toricity of the sclera, but of course, in the absolute value in the sag calculator, you cannot mask anything. So let's call it the real values will always come out, and so the 780 micron difference that we calculate there are the real deal.
Mm-hmm. Would you want to pop back to the previous case too for just a moment?
Sure. Yeah. So the number one case, bear with me. Yeah. So that'll be this one. Yeah.
Right. And so the question was, the choice of APS on this patient. Can you talk about how that's generated here again? Just you have APS of 6 and minus 10.
Yeah. So the 6, as I mentioned, basically what it does, it'll take so for this, I'll switch to the results. Oh, sorry, I need to click on the other screen, bear with me. And then go to the tangent angles map. So these are the local slopes. And so it will look at the tangent angles in the landing zone of the sclera on the periphery of that scleral lens, and match those with the back surface angles of the Zenlens. Mm-hmm. And it's a little bit tricky to back calculate that, as I mentioned. But if we go to then the toricity, here we can actually do some calculations. So if we were to go to results, go to the sag calculator and fill in chord length 16. We again then turn to the min sag and the max sag. Min sag is at 4.20 millimeters and the max sag is about 4.71. So a difference of around about 500 microns. And so on the basis of that, you can back calculate the actual difference in APS between the steep and the flat.
Right.
So that's similar to how I showed that for the second example.
Correct.
So and we feel it's really important, of course, that all of our users, the doctors out there, they do more than just rely on the automated results from an algorithm. They actually understand what the basic principles that are behind it are.
Correct. Yeah, that's very helpful. Thank you. And then I guess, if there's any questions going forward, you have your contact information again.
Absolutely.
And if anybody, you can sure pass on my contact information as well if anybody needs it.
Fantastic. Thank you.
Okay.
Yeah. Okay. Well, thanks for all the good questions, and thanks, Dr. Jetica, for bringing that to notice. Because and I hope we've filled in a lot of gaps, and no doubt we've opened up a few more. But we'd love to have the dialogue with you guys, and I look forward to hearing from you. Thank you.
Thank you.